Hello, my name is Kishla Singh. This presentation is for the mid-semester project evaluation for the subject Galactic and Extragalactic Astronomy. So I guess I've already announced my name. My topic is James Webb Space Telescope. So yeah, let's start with the presentation. So the James Webb Space Telescope, also known as JWST or Webb Telescope in public lingo, is a space telescope that is planned to be the successor of Hubble as well as Spitzer Space Telescope, and it is also designated as the NASA's flagship astrophysics mission. It is yet to be launched, not yet launched. It is yet to be launched in the month of October this particular year. So this is how it looks being in full size, being unfolded. I'll discuss about each part and how it functions in detail in the further slides. So how it is better than Hubble? So JWST will provide improved infrared resolution and sensitivity over Hubble. However, Hubble was primarily a UV optical and a near infrared telescope, uh, which the advantage will enable us to investigate a broad range of topics in astronomy and cosmology. We will able to see objects like first galaxies that are being formed at the very edge of our observable universe. So let's talk about its features. There are many features of this space telescope, but what stands out the most, I'll be talking about that. So let's start with the sun shield protection. Uh, so the sun shield is the primary objective of this particular protection is to, as the name suggests, is to protect the radiation, that is IR radiation that comes from the sun. So that in order to prevent the interference and the noise creation in the data collected. So the JWST instruments are kept meant to be kept under 50K for observation. So uh, so there is a five layer sun shield which is each as thin as human hair, is constructed with aluminum on both sides and doped with silicon on the sun facing side of the two hottest layer to reflect the sun's heat back into space. The sun shield is designed to be folded 12 times so that it will fit within the Ariane 5 rocket, which is a European Space Agency's rocket. So the problem is that the area, the full area is of the shields are so high that it couldn't be placed into a payload fairing of any rocket. So it is being folded in a fashion that it accommodates itself into the payload of a rocket. So this is just a animation of how this the unfolding happens. As you can see, yeah, you can see how the wing expands and every sheet stretches itself out. So let's talk about the optics. So GW's primary mirror is a 6.5 meter gold-plated, gold-coated beryllium reflector with a collecting area of 25.4 meters square, which is about 6.25 times the collecting area of Hubble. The mirror is so large that it is being decomposed into 18 hexagonal segments so that it could be, as I said in the earlier slides, it could accommodate itself into the payload fairing of a rocket. So there is something called active optics installed to take care of the optical aberrations over a wide field to produce sharp images. So yeah, so this is how the mirror unfolds. This is a very nice animation on the both sides of the whole mirror. Yeah, okay. So scientific instruments on board. So the integrated science instrument module, which is also known as ISIM, is a framework that provides electrical power, computing resources, cooling capability, as well as structural stability to the Webb telescope. NIRCam, near infrared camera, is an infrared imager which will have a spectral coverage ranging from the edge of the visible to the near infrared. zero point 0.6 micrometer corresponds to the orange color and 5 micrometers in the near infrared spectrum. NIRSPEC, which is a near infrared spectrograph, which is an onboard spectrography machine which will enable us to decompose the matter content from which the light is coming. The MIRI, the mid-infrared instrument, will enable us to perform mid-infrared to long infrared wavelength range, that is from 5 micrometers to 27 micrometers. It also includes a imaging spectrometer. So and the last instrument, which is the GS near ISIS, near ISS, uh, it is a kind of stability system which enable us to perform to keep the sensor in the line of sight of the observation point, even if the instrument moves here and there. So this is how all the instruments are accommodated on board of the telescope. There are many other instruments as well, but these are the four main components which takes care of the majority of the work happening on the telescope. The cost and the schedule, and why is it taking so long? So here you can see in the table, you can see when it was the year 1997, which was when I was born, when it was scheduled to start working on it, and the budget was about $500 million. But right now, about this particular year, it has gone over a budget of $10 billion, which is approximately $11.5 billion, and it's taking a lot of time and money to construct it. It is taking a lot of time because, as we can see on Hubble, astronauts were able to perform an onboard repair and instrument swapping tasks. But since this telescope is placed so far from Earth, that it is impossible for astronauts to perform any necessary maintenance or upgrading on the telescope. So so the scientists have to make sure that every and each instrument is performing very well, even after going through all the launch and the unfolding of the mirrors, launched vibrations and unfolding of the mirrors. So let's talk about its mission. Yeah, mission impossible yet, because it is not a we are not able to launch this telescope yet. So it has four key goals: to search the light from the first stars and galaxies that formed in the universe after Big Bang, to study the formation and evolution of galaxies, to understand the formation of stars and planetary systems, and to study planetary systems and the origins of life. The mission is to, for this reason, JWST instrument will not measure visible or ultraviolet like Hubble telescope, but will have a much greater capacity to perform infrared astronomy. Why infrared? I will talk about this in later slide. The JWST will be able to have a sensitive range of 0.6, which is orange light, to 28 micrometers, which lies in a deep infrared spectrum. So let's talk about the mission details, like how it is going to be launched, orbit, infrared astronomy, and how the people on the ground will able to control it. So the launch is meant to be happen on Ariane 5 rocket, as I already said, which is a French rocket, which is an ESA's rocket, a European Space Agency's rocket from French Guiana. The telescope is not serviceable, and astronauts would not be able to perform tasks such as swapping instruments as with happened in the Hubble telescope. I also discussed this. It expected planned mission time is about 5 years, with the goal of 10 years in back. JWST needs to use propellant to maintain its halo orbit around L2. I'll discuss what this L2 is, which provides an upper limit to its designated lifetime. So the orbit is actually so let's talk about its orbit, where it is exactly placed. So there are 5 Lagrangian points in any two gravitating body system. So these points are the places where the potential is such that the time period of the particle or an object placed at that particular point is same as that of Earth. In this case, it is placed at a point known as L2, which is about 1,500,000 kilometers away from Earth and from the Sun. It is like Sun, Earth, and then the space telescope. So what happens? I should able have an animation here. Yeah. So here you can see what happens then. The combined pull of Sun and Earth makes the telescope have the same time period as that of Earth. Yeah. So there is a halo orbit. Why this is called a halo orbit? Because the L2 point is not a stable equilibrium. The telescope needs to able to continuously orient itself at that particular point, so that it doesn't drift itself. So it has an onboard a thrust system, so that it continuously helps itself to be orbited, to be placed at that particular point, which results in a halo orbit. Yeah, this is the animation I was talking about. You can see how the telescope is being revolving around a point, which is which is the point called L2, the Lagrangian point 2. So yeah, as said above, we will discuss about the infrared astronomy. So why infrared? Because infrared is such a wavelength that is able to penetrate through dust and gas. This allows us to allows us the observation of dimmer and cooler objects, uh, which is basically the objects being first formed at very far at the edge of the observable universe. Since water vapor and carbon dioxide in the Earth's atmosphere strongly absorbs infrared, also Earth's surface radiate a lot of IR radiation. It makes sense to have a space observatory in space. The more distant an object is, the younger it appears. Its light has taken longer to reach human observers because the universe is expanding. As light travels, it becomes redshifted, and the object at extreme distances are therefore easier to see if viewed in infrared. JWST's infrared capabilities are expected to let it see back in time to the first galaxies forming in about a few 100 million years after Big Bang. This feat has never been achieved by any of the telescopes in history. So you can see here there is a this is just animation. Right now it is an optical picture, and this converts back into the infrared. Here you can see much deeper in infrared spectrum than it was in optical, because due to the presence of dust and gases which blocks infrared light. So the ground support and operation. The Space Telescope Science Institute (STSCI), located in Baltimore, Maryland, on the Homewood campus of Johns Hopkins University, was selected as the Science and Operations Center for JWST. Similar to how Hubble is operated, anyone anywhere in the world will be able to allowed to submit proposals for observation. The bandwidth and the digital throughput of the satellite is designated to operate at 458 gigabits of data per day, which is a huge data to analyze for the length of the mission. So after launch deployment, how will it be launched, and how much time will it take to fully start taking data after being launched from the Earth? So this is the whole timeline. Here is Sun, here is Earth, and it's going to go away from Earth at a point 1.5 million kilometers away from Earth at a point L2, and it will simultaneously deploy its wings, its mirror, and start taking data after a month of deployment. So here you can see a polar view of the trajectory of how will it rotate, how will it orient itself for data taking. The blue dot here is the Earth, and this is the halo orbit which I was talking about. This is actually a kind of a geostationary stuff for the Earth. As like geostationary, how geostationary satellites are placed for Earth. This is how the L2 point is always being close to Earth, even for the throughout the year. This is the equatorial view. You can see there is a slight inclination to the plane of Earth-Sun motion, Earth-Sun plane of motion. These are the countries involved in this. This is a giant collaboration of very huge country, mainly Europe and America. And yeah, here it concludes my presentation. Here are my references. So thank you so much.